Have you ever wondered how engineers get a clear picture of a dynamic system's stability and performance, especially when there is feedback involved? It is like having a crystal ball that shows you how your system will behave under different conditions. A Nyquist plot is a powerful graphical tool that helps you do just that. It is constructed directly from a system's open-loop transfer function and provides an intuitive visual representation of stability in the complex frequency domain. The core idea behind the Nyquist plot is to visualize the frequency response of a system in the complex plane, which then allows you to apply the Nyquist stability criterion. This criterion helps determine the stability of a closed-loop system based on the plot of its open-loop transfer function, specifically by observing how it encircles a critical point. Understanding this visual feedback mechanism is essential for designing reliable control systems. To construct a Nyquist plot, you first take the open-loop transfer function of your system, which is typically represented as g of s h of s. Next, you substitute the complex variable s with j omega, where j is the imaginary unit and omega represents the angular frequency. This step converts your transfer function into its frequency response. Then, you vary omega from 0 to positive infinity. For each value of omega, you calculate the magnitude and phase of g of j omega, h of j omega. You then plot these complex numbers on the complex plane, where the horizontal axis represents the real part and the vertical axis represents the imaginary part. This gives you the plot for positive frequencies. To complete the plot, you reflected the positive frequency curve symmetrically across the real axis to obtain the plot for negative frequencies, from negative infinity to 0. If your system has any poles at the origin, you will need to add a small semicircular detour of infinite radius around the origin for the plot, to accurately representing the transfer function's behavior near s equals 0. Once the plot is complete, you can identify important characteristics like the gain margin and phase margin. These are crucial indicators of a system's relative stability and robustness. Gain margin tells you how much the gain can increase before instability, while phase margin indicates how much phase lag can be introduced before instability occurs. Ultimately, the Nyquist plot is not just about identifying whether a system is stable or unstable. It is about gaining a deep understanding of its dynamic behavior and its resilience to changes. This powerful visualization allows you to design and fine-tune control systems that are not only stable but also robust and perform exactly as intended, even in challenging environments.